Hey guys, my name is Annika, and this is Chapter 17 of Holt Physics, which is Electrical Energy and Current. This chapter is going to be broken down into four main segments. First we'll cover electric potential, then we'll look at capacitance, current and resistance, and electric power. So in this first video, I'll be covering Chapter 17.1, which is electric potential. So I discussed before that electrical force is similar to gravitational force in that it is a field force. Electricity is also similar to gravitational force in that it has potential energy associated with it. So electrical potential energy is defined as the energy associated with a charge due to its position in an electric field. And basically what that means is that we're going to have to account for electrical potential energy when we're adding up the total mechanical energy. So as I've written below, mechanical energy will now be equal to kinetic energy, which we learned about before. That's energy that results from the object's motion, plus gravitational potential energy, which I've written as Pe sub g, plus elastic potential energy, which is kind of like in a situation with a spring that's causing an object to move. And finally, we'll add on this last component, which is electrical potential energy, or Pe electrical. Here you can see the equation for electrical potential energy in a uniform field. Essentially what the uniform field part means is that the field has the same value and the same direction at all points. So that just refers to how the electric force is moving. So we write that the electric potential energy, or Pe electric, is equal to negative QEd, where Q is equal to the charge, E is equal to the strength of the electric field, and D represents the displacement from a reference point in the same direction that the field is moving. And the unit for all of this is the joule, which we write as J. That's the same unit that we use for all types of energy. Electric potential describes the work that must be performed against electric forces to move a charge a certain distance, and then that's all divided by the charge. So electric potential is represented as a V, and then that equals Pe electric, or electrical potential energy, divided by Q, which is the strength of the charge. So this essentially allows us to calculate a charge's potential independently of the size of the charge. So since we're dividing by this Q on the bottom, it shows that this electric potential is the result of other charges surrounding a charge, but it does not depend on the strength of the charge itself. When the electric potential of a charge changes, this is known as potential difference, which is used to express the work that must be done to move a charge between 2 points. And then again, this is divided by the charge to make the quantity independent of the charge's magnitude. So we write potential difference as delta V, or essentially a change in potential. And then that equals the change in electric potential energy divided by Q, or the magnitude of the charge. And the units for potential difference are volts, or V, where a volt is equal to 1 joule per coulomb. And this makes sense because electric potential energy, as I said before, is expressed in joules, and charge is expressed in coulombs. And to clarify once again, electric potential is energy per unit charge, whereas potential difference is the change in energy per unit charge. So essentially, potential difference is the change in electric potential between two positions of a charge. So as I mentioned before, electric potential energy is equal to negative QEd, or negative charge times the strength of the electric field times displacement. We also know that this delta V, or potential difference, is equal to the change in potential energy divided by the charge. That's another equation that we've gone over. So now if we plug in this expression for the change in potential energy, we would get that the potential difference is equal to delta negative QEd divided by Q. As you can see, the Q's would cancel, and we're left with delta V equals negative Ed. So in other words, the potential difference in a uniform electric field is equal to the negative magnitude of the field times displacement. So because electric potential does not depend on the charge of the reference point, it can exist at any point in a field regardless of whether there is a charge at that point. So essentially, electric potential only depends on the magnitude of the charge that's responsible for creating it, not actually on the charge that we're using as a reference point. So let's take this example where we have two charges. We have Q1, which is at point A, and then we have Q2, which is at point B. And we have some distance between them, which we'll call R. In this case, we'll use the equation for the potential of A, which is equal to the electric potential energy divided by Q1, which is the strength, again, of charge at A. So we can substitute in this equation where electric potential energy equals Coulomb's constant times Q1, Q2 divided by R, and then we'll move over this Q1. As you can see, the Q1s would cancel, and we get that the potential at A is equal to Coulomb's constant times Q2 divided by R. Or in other words, Coulomb's constant times the strength of the force responsible for the charge, which is the charge at B, divided by R, which is the radius between the 2 points. So the equations that we derived from points A and B allows us to determine the potential difference between a point at infinity and a point near a charge. So essentially what this means is we're imagining this point that's out at infinity effectively so far away from the field that it's experiencing no charge because this denominator of radius is so high. So it's the difference between that point and a point near a charge. So we'll write this as delta V, or potential difference, equals Coulomb's constant times Q, which again is the charge, divided by R, which is the distance from a reference point. So this is similar to the equation on the last slide, but it allows us to describe potential difference rather than simply potential. So finally, when we're looking at electric potential, we can apply the superposition principle, which I introduced in the last chapter. This applies to situations in which multiple charges surround a reference point. So essentially what this means is that in order to calculate the net charge, you would add the total electric potential at each point. So if we're using this point in the center, we would have to add the electric potential of each of these charges to find the total potential, and that's known as the superposition principle. So with this information in mind, here are some practice problems. Number 1. As a particle moves 10 meters along an electric field of strength 75 newtons per coulomb, its electrical potential energy decreases by 4.8 times 10 to the negative 16th joules. What is the particle's charge? So we have our equation for the change in potential energy, which we'll call delta PE electric. That's equal to negative QED, which again is the charge times the strength of the electrical field times the displacement. So we've learned that the change in potential energy, it's a decrease, so it's negative 4.8 times 10 to the negative 16th joules. That's equal to negative, Q is what we're solving for because it's asking for charge. The strength of the electric field is 75, and then it's moving 10 meters, so that's the displacement. So now if we divide both sides by 750 to get rid of the 75 and the 10, we get that the charge is equal to about 6.4 times 10 to the negative 19th coulombs. Number 2. An electron, which has a charge of negative 1.6 times 10 to the negative 19th coulombs, moves 4.5 meters in the direction of an electric field with a strength of 325 newtons per coulomb. Determine the change in electrical potential energy. So we'll be using the same equation from the last problem, where this change in potential energy equals negative QED. We're looking this time for the change in potential energy. We know that the charge is negative 1.6 times 10 to the negative 19th. So since it's negative here, we'll write this as positive 1.6 times 10 to the negative 19th coulombs. The strength of the field is 325, and then the distance that it moves is 4.5. Now that we have all of this information, we'll simplify to find that the change in potential energy, or delta PE, is equal to about 2.34 times 10 to the negative 16th joules.